This video is brought to you by Group 9 from Section B11. The members are Joervie P. ADANTE, Aulivier Gilchrist Aquino, Jarren S. BAYLON, and Denise L. BURGOS. We present to you Topic 14, Optical Communication Systems.
Have you ever thought about how you get emails or any other information from any corner of the world within a blink of an eye? This has been made possible by a network of cables, which are laid under the ground and below the ocean. The cables, which carry most of the world's data, are optical fiber cables. They are also used in medical equipment. Let's learn how optical fiber cables work and how they have revolutionized the world around us. Optical fiber cable is made up of thousands of fiber strands, and a single fiber strand is as thin as a human hair. Optical fibers carry information in the form of light. Let's first learn some fundamental behaviors of light to understand the workings of optical fibers. The speed of light changes when it passes through a medium, and this change in speed is expressed by the refractive index. This variation in the speed of the light leads to another interesting phenomenon: refraction. To understand what it is, let us carry out an interesting experiment. In this experiment, light passes through a prism. You can see that at the interface, the light gets bent instead of going straight. This phenomenon is known as refraction. Refraction occurs when light passes from a medium with one refractive index to one with another refractive index. The light bends towards the interface when it goes from a medium of high to one of low refractive indices. Refraction is the reason why a pencil looks bent in a glass of water. This simple refraction technique is effectively used in optical fibers. Now, let's make this experiment a hypothetical one. Using some dopants, we are able to increase the refractive index of the glass in real time. As we increase the refractive index, the light will bend more and more towards the surface. After a time, you can see that the light will pass through the surface of the glass. If we increase the refractive index further, the light will suddenly come back to the first medium as a pure reflection. This is called total internal reflection. The total internal reflection is possible if we increase the incident angle rather than increasing the refractive index. In this case, at a certain angle called the critical angle, the light will come back to the first medium. This phenomenon of total internal reflection is used in optical fiber cables to transmit the light. The simplest form of optical fiber cable is shown here: cylindrical glass with a high refractive index. If the laser strikes the interface at an angle greater than the critical angle, total internal reflection will happen, and the light will reach the other end. This means that light can be confined in the optical fiber over a long distance, no matter what complex shape the fiber forms. Remember, total internal reflection happens between the high refractive index glass and the low refractive index air. However, optical fibers need a protective coating. A protective coating is not possible with this configuration. The introduction of protective material will replace the position of the air and cease the total internal reflection phenomenon. An easy way to overcome this issue is to introduce a low refractive index glass above the core glass, known as cladding. This way, total internal reflection will happen and we'll be able to use a protective layer. Both the core and the cladding use silica as their base material. The difference in the refractive index can be achieved by adding different types of dopants. The optical fiber we have just constructed won't be able to carry signals for more than 100 kilometers. This is due to various losses that happen in the cable. This loss of signal strength is generally called attenuation. Absorption and scattering are the main reasons for signal attenuation. This is why you see amplifiers in cables after a certain distance. They boost the signal strength and allow signals to be transmitted over a long distance. The power required for the amplifier is drawn from nearby sources. Now, back to the main topic. How does the optical fiber transmit information such as phone calls or internet signals? Any information can be represented in the form of zeros and ones. Assume you want to send a hello text message through your mobile. First, this word will be converted into an equivalent binary code as a sequence of zeros and ones. After the conversion, your mobile phone will transmit these zeros and ones in the form of electromagnetic waves. One is transmitted as a high frequency and 0 as low frequency wave. Your local cell tower picks up these electromagnetic waves. At the tower, if the electromagnetic wave is of high frequency, a light pulse is generated. Otherwise, no pulse is generated. Now, these light pulses can easily be transmitted through optical fiber cables. The light pulses which carry the information have to travel through a complicated network of cables to reach their destination. For this purpose, the entire globe is covered with optical fiber cables. These cables are laid under the ground and below the ocean. It is mainly the mobile service providers that maintain these underground cables. AT&T, Orange, and Verizon are some of the few global players who own and maintain the submarine cable network. A detailed cross-section view of an undersea cable is shown here. You can see that only a small portion of the cable is used for holding the optical fiber. The remaining area of the cable is a mechanical structure for protection and strength. Now, the question is, where does the amplifier get power from under these deep oceans? Well, for this, a thin copper shell is used inside the cable, which carries electric power along the cable so that the amplifiers can be powered. This whole discussion simply means that if optical fiber cables do not reach a part of the globe, that part will be isolated from the internet or mobile communications. If we compare optical fiber cable to traditional copper cable, the optical fiber cable is superior in almost every way. Fiber optic cables provide larger bandwidth and transmit data at much higher speeds than copper cables. This is because the speed of light is always greater than the speed of electrons. The flow of electrons in a copper cable generates a magnetic field, even outside of the cable, that can cause electromagnetic interference. On the other hand, the light, which travels through the optical cable, is always confined within the fiber. Thus, the chance of interaction with an external signal does not exist. One more interesting feature about optical fiber cables is that any light signal which enters from the side has a minimal chance of traveling along the cable. Thus, the optical fiber cables provide high data security. You might be amazed to know that optical fiber was first used in endoscopy, even before it was used in the telecommunications field. In telecommunications, digital pulses are transferred through the optical fiber cable. However, in endoscopic cables, visual signals, which are in the analog form, are transmitted to the other end. We request your support at patreon.com to help us continue our education services, and thank you for watching the video.
So now, we will be talking about fiber optics, specifically its definition, and we will review optics. First, let us define what optics is. So optics is the branch of physics that studies light, specifically its behavioral pattern and individual properties. So now, what are fiber optics? Fiber optics refer to the medium and the technology associated with the transmission of information as light pulses along a glass, plastic strand, or fiber. Fiber optics are used in long-distance and high-performance data networking. Next is light. Light is a form of energy that is in the form of an electromagnetic wave. Light frequency falls between those of microwaves and X-rays. So talking about light, we will now discuss the speed of light. So the speed of light is 2.998, approximately 3 times 10 raised to 8 meters per second. So the speed of light is slower as light passes through a material such as glass, water, or plastic. Now, we will talk about the wavelength and the frequency of light. So light can be distinguished with its frequency, but light is rarely expressed as frequency. Instead, it is often expressed in terms of wavelength. So to give you a brief definition, frequency is the number of cycles per second and is expressed in the units of hertz. On the other hand, wavelength is the distance between the peaks of the waves. The relationship between lambda, or the wavelength, and frequency is given by this equation. Lambda is equal to c over f, where c is the speed of light and f is the frequency. Now, angstrom is also another measure of light wavelength. Next, we have the optical spectrum, as shown in the figure. This includes the visible light, infrared, and ultraviolet. This will be discussed in the following slide. Now, let us further discuss the optical spectrum. So first is violet, which is the short wavelength light and is approximately 400 nanometers. Next is red, which is a long wavelength light, approximately 700 nanometers. Followed by red is the infrared, which is below visible light and is approximately 0.7 to 1000 micrometers. This can be divided into the near or far infrared. The near infrared is near the optical spectrum, while the far infrared is lower in frequency and is close to the upper microwave region. Lastly, the ultraviolet range. This is above visible spectrum, above visible violet light, and is approximately 400 nanometers to about 10 nanometers. Now, the sun is a primary source of UV light. Next, we will talk about physical optics. So, physical optics refer to the ways that light can be processed or manipulated. Now, light waves can be focused, enlarged, reflected, or refracted. So first, let us talk about reflection. So reflection, as defined, is the change in direction of light at a boundary between two different media so that the wavefront returns into a medium from which it was originated. Now, reflection is the simplest way of manipulating light. Here, light rays are thrown back or reflected by a reflective surface such as a mirror. In reflection, we have the normal line. This line is perpendicular to the reflective surface and is usually drawn from the point where light is reflected. Next, we have the incident ray. This is simply defined as the light ray from the light source. We also have the angle of incidence. This angle of incidence is the angle that the incident ray makes with the normal line. Here, we also have the reflected ray. This reflected ray is the light ray reflected between the surface. With the reflected ray, we have the angle of reflection. This angle is the angle that the reflected ray makes with the normal. Lastly, we have the law of reflection. Now, the law of reflection states that the angle of incidence is equal to the angle of reflection. So now, let us move on to refraction. So as defined, refraction is the bending of light as light passes from one medium to another. This occurs when light passes through a transparent material such as air, water, and glass. Furthermore, refraction takes place where two different substances meet. With refraction, we have the boundary. The boundary is also known as the interface, or the dividing line between two different substances. Next, we have the index of refraction. This is denoted as n and is defined as the measure of amount of refraction of light. This is also the ratio of the speed of light in air to the speed of light in the substance. Now, this index of refraction is unique for every substance, and it is also a function of light wavelength. Now, light bends according to the refraction index. So here, we have the refraction index. For air, it is 1. For water, it is approximately 1.3. And for glass, it is 1.5. We also have the angle of refraction. Now, the angle of refraction is the angle between refracted ray and the normal. So here, we can see the relationship between angle A and angle C, wherein n sub 1 sine A is equal to n sub 2 sine C. Furthermore, we have the critical angle. So the critical angle is the value of the angle of incidence in which the refracted ray is 90 degrees to the normal. So the refracted ray travels the interface of the two substances. The critical angle is dependent upon the index of refraction. When the angle of incidence is less than the critical angle, the light ray gets refracted. When the angle of incidence is greater than the critical angle, the light ray gets reflected. Lastly, we have the total internal reflection. This is the complete reflection of light because the angle of incidence increased further than the critical angle. This is the basic principle that allows a fiber optic cable to work.
Now, we are going to talk about optical communication systems, its definition, free space and fiber optic communication system. Fiber optics is about optical communication systems whose medium is the fiber optic cable. Free space optics of FSO is about optical communication systems whose medium is free space. The reason why light is used for communication is because the use of light vastly increases the bandwidth. Optical communication systems use light as the carrier of the information to be transmitted. Medium may be free space or fiber optic cable. The figure shows the light wave communication in free space. The light source functions as transmitter, for example, the LEDs and lasers. It can also follow electrical signals as fast as 100 GHz. The lasers generate monochromatic or single-frequency light that is fully coherent. Lasers thus produce a very narrow and intense light beam as all the light waves are lined up and sync. It also makes the optical communication more practical. The high-intensity and single-frequency light source. It is a narrow beam of light with a specific wavelength or color. It can penetrate atmospheric obstacles better than other types of light can, thereby making light beam communication more reliable over longer distances. Because of the narrow beam light, transmitter and receiver must be perfectly aligned. Misalignment produces loss that will be discussed in another section of this presentation. Modulator vary the intensity of the light beam in accordance with can use AM or PM. In AM, the brightness varies continuously, and in PM is where the light simply turns off and on. In amplitude or intensity modulation, the information or intelligence signal controls the brightness of light. For analog signals, brightness varies continuously over a specified range. This is used in some cable TV systems. Pulse modulation is used for digital signals. The light beam simply turns off and on. Digital modulation usually uses NRZ formatted binary data producing off-on keying or OOK or amplitude shift keying or ASK. In pulse modulation, the light beam turns off and on in accordance with some special binary signal commonly in NRZ, RZ, and Manchester formats. Frequency modulation is not used in light communication. There is no practical way to vary the frequency of a light source. For analog signals, The modulator can be a power transistor in series with the light source and its DC power supply as shown in the figure. The receiver. Photodetector that picks up the modulated wave. It can be a photodiode or transistor whose conduction is varied by the light. Small signal is received and is amplified and then demodulated to recover the originally transmitted signal. Digital processing may be necessary. As an example, for PCM or A or D and D or A converters is needed at the transmitter and receiver respectively. For example, the A or D converter digitizes an original signal before being transmitted as a PCM signal. The D or A converter will be needed at the receiver to recover the voice signal. Fiber optic communication system uses fiber optic cables as the medium, has wide bandwidth, and multiplexing can be incorporated in the system for an almost limitless capacity for information transfer.
Optical communication systems, components, application, advantages, and disadvantages. These are the fiber optic components of a communication system. In the system, the first step uses an AD converter to convert the analog signal to digital pulses. In some systems, there are voltage to current converters before and after the DA or AD converter respectively. The voltage to current converter serves as an electrical interface between the input circuitry and the light source. Digital pulses are used to flash a powerful light source off and on very rapidly. In simple low-cost short-distance systems, light source is the LED that emits low-intensity infrared light beams. The source-to-fiber coupler, a mechanic interface, is added before transmitting another system. This coupler is used to couple the light emitted by the source into the optical fiber cable. Light beam pulses are fed into a fiber optical cable, which is transmitted over long distances. In other systems, a fiber-to-light detector is used as a couple as light as much possible for fiber cable into light detector. At the receiving end is a photocell or light detector which detects the light pulses and converts it to an electrical signal. Electrical pulses are amplified and reshaped back into digital form. The last step is the DA converter that acts as a decoder to convert the digital electrical pulses to the original voice or video. In other models, there is an interface between the fiber end and the light source, and between the other fiber end and light detector. Its applications are TV studio to transmit interconnection, eliminating a microwave radio link. Closed-circuit TV systems used in buildings for security. It secures communication systems at military bases, computer networks, wide area, metro, and local area, shipboard communication, and lastly, it is also used for aircraft communication or conference. Other applications are interconnection of measuring and monitoring instruments in plants and laboratories, data acquisition and control signal communication in industrial process control systems, nuclear plant instrumentation, college campus communication, also utilities, specifically electric, gas, and so on, station communication. Also, it is used for cable TV systems, replacing coaxial cables, used for the internet, black hole for cellular-based stations, the DAS or distributed antenna system, connections between servers, routers, and switches in data centers, and connection between the cellular base station and the remote radio head mounted at the antenna. For the advantages, it is easy to install, wider bandwidth, fiber optic cables have higher information carrying capability, low loss means fiber optic cables have less signal attenuation over a given distance than an equivalent length of coaxial cable. It is lightweight. Glass or plastic cables are much lighter than copper cables and offer a benefit with low weight is critical. Small size. Practical fiber optic cables are much smaller in diameter than electrical cables and thus can be contained in a relatively small surface or space. Security. Fiber optic cables cannot be easily tapped as electrical cables and they do not radiate signals that can be picked up for eavesdropping purposes. There are less need for complex and expensive encryption techniques. Interference immunity. Fiber optic cables do not radiate signals as said earlier as some cables do and cause interference to the other cables. They are immune to the picking up of interference from other sources. They are immune to crosstalk between cables caused by magnetic induction and also immune to static interference caused by electrical noise surfaces or sources. Greater safety. Fiber optic cables do not carry electricity and therefore there is no shock hazard. They are also insulators and thus not susceptible to lightning strikes and electrical cables are. They are also corrosive and or explosive environments without danger of sparks. Protection from environmental factors. Resistive to environmental sources since they operate over a large temperature variation. Inexpensive maintenance. Long-term cost is less than the metallic counterpart. Its disadvantages are high initial cost, more fragile compared to electrical wires, high maintenance, light is attenuated and dispersed as transmission distance gets longer, greater attenuation and dispersion as distance increases, and lastly, unidirectional light propagation.
Let's move on to section 4. In this section, we will be talking about fiber optic cables. Here is a picture of fiber optic cables. You can see the light at the ends, but the light used in fiber optic cables does not necessarily need to be within the visible light. So in some cases, the light propagating inside the cable might not actually be seen. A fiber optic cable is a thin glass or plastic cable that acts as a light pipe. It is not a hollow tube carrying light, but a long thin strand of glass or plastic fiber. It has a circular cross-section with a diameter that is only a fraction of an inch. Some are the size of human hair. The light propagates through the fiber following the laws of optics. Let's talk about how fiber optic cables work. The picture shows different light beams propagating in different paths. For light beam A, it enters perpendicularly at the end, and after entering, light beam A travels straight and exits the other end. For light beam B, it did not get reflected and it escaped outside the fiber optic cable. This is because the angle of incidence is less than the critical angle, thus it gets refracted. Light beam C and D has an angle of incidence that is greater than the critical angle, thus total internal reflection occurs. And since the angle of incidence will be the angle of reflection, it will be able to get reflected again. Light beams C and D bounces back and forth between the surfaces until it exits at the other end of the cable. In the prior figure, total internal reflection was observed. The total internal reflection occurring
follows the principles of reflection. Thus, light rays entering at different angles will take different paths and will have different traveling time. Here is a picture of a construction of a fiber optic cable. Cables vary in the number of fibers. Simple cables have a single strand of fiber, while complex cables have multiple fibers. The glass or plastic portion of the fiber optic cable carries the light. This is called the core. Silica is just another name for glass. Comparing glass and plastic, glass has superior optical characteristics but expensive and fragile. Plastic is less expensive and more flexible but has greater attenuation. Furthermore, light will travel a farther distance in glass than in plastic. The core, which is the fiber, is surrounded by a protective cladding. Within the cladding is the glass or plastic optical fiber contained. It has a slightly lesser index of refraction than that of the core. The core index of refraction is denoted as n sub 1. The cladding index of refraction is denoted as n sub 2. 1.5 and 1.4 is the typical value of n sub 1 and n sub 2. PCS cable, short for plastic clad silica cable, is a glass core with a plastic cladding. Typically, division between the core and the cladding cannot be seen as they are usually made of the same type of material. Jacket. Over the cladding is a plastic jacket. It is made of some type of plastic such as PVC or polyvinyl chloride, polyethylene or polyurethane. It protects the core and cladding from damage. It minimizes physical damage such as cuts, nicks, and crushing. It protects from moisture, dirt, temperature variations, and other conditions because fiber optic cables are usually buried underground or strung between supports. There can also be 2 or more elements added in a fiber optic cable besides core, cladding, and jacket that makes up the simplest cables. Typical cables are available with 2, 6, 12, 18, and 24 optical fiber cores. Kevlar. Kevlar is a special yarn that makes a strength member which helps minimize damage to fiber optic elements when the cable is being pulled or must support its own weight. The picture on the left shows the angles as the light propagating through the fiber optic cable gets refracted and reflected. As light enters the fiber, the angle of incidence is expressed as theta in. Since light will be passing the air-glass interface, wherein the glass is more dense than the air, from Snell's law, light will refract towards the normal. In other words, light will travel closer to the normal after refraction. The angle of refraction is shown as theta 1. It will strike the cladding at an angle of theta c. Light must strike the internal core or cladding interface at an angle greater than theta c, or the critical angle. This happens when the angle of incidence is within the angle of acceptance. Angle of incidence must be less than the angle of acceptance as it enters the light fiber. This ensures that the light strikes the core and cladding interface at an angle greater than theta c. Note in the figure that theta c and theta 1 is complementary as they are 2 angles in a right angle. The acceptance cone is shown on the right. If the light ray entered the cable within this cone, then it will undergo total internal reflection. Let us try to derive the angle of acceptance. Equation 1 is simply the Snell's law as the light gets refracted upon entering from the external medium to the core. N0 is the index of refraction of the external medium, as N1 is the index of refraction of the core material. Equation 2 is taken from the fact that theta 1 and theta c is complementary as I have mentioned before. Substituting equation 2 in sine theta 1, we get equation 3. Sine theta 1 is equal to sine 90 minus theta c, which is equal to cosine theta c. Therefore, sine theta 1 is equal to cosine theta c, which can be substituted to equation 1 to get equation 4. Theta in became theta in max in equation 4 because this is the maximum angle that a light ray can enter the fiber optic cable. Upon entering and getting refracted, it will strike the core and cladding interface at the critical angle. Below theta in max, the light ray will strike the core and cladding interface more than the critical angle, and total internal reflection will occur. If theta in is greater than theta max, the light ray will strike core cladding interface at an angle less than the critical angle, and total internal reflection will not occur, and the light will get refracted. The critical angle can be computed using equation 5. Theta c is equals inverse sine of n2 over n1. We can then construct a right triangle. Sine of an angle is the ratio of the opposite side over the hypotenuse. The opposite side is n2 and the hypotenuse is n1. The adjacent side is derived using the Pythagorean theorem. Cosine of the critical angle can then be taken from the triangle. The formula for cosine theta c is shown in equation 6. We can substitute equation 6 in equation 4. Equation 4 and 6 is shown again to show the substitution. Equation 7 is the result of the substitution. n1 will be cancelled. Isolating theta in max, we get equation 8. Equation 8 gives the formula for the angle of acceptance. Generally, light enters the fiber from an air medium. This is why n0 can be taken as 1, their index of refraction of air, and you might see equation of the acceptance angle with the n0 already omitted. Numerical aperture of fiber optic cables is a number less than 1 that measures the light gathering or light collecting ability of an optical fiber. Typical numerical apertures for common cables are 0.275 and 0.29, mathematically defined as the sine of the angle of acceptance. It is Na equals sine theta in max, which is equal to the square root of the difference of the squares of n1 and n2. Sample problem number 1. The numerical aperture of a fiber optic cable is 0.21. What is the angle of acceptance? Numerical aperture can be computed by sine theta in max, or the sine of the angle of acceptance. Isolating theta in max, we get theta in max equals the inverse sine of the numerical aperture. We can then substitute the value of the numerical aperture, which is 0.21. The inverse sine of 0.21 is equal to 12.12 degrees. The angle of acceptance is 12.12 degrees. Sample problem number 2. 1.55 is the index of refraction of the core, and 1.45 is the index of refraction of the cladding. The light source enters the end of the fiber from an air medium. What is A, the angle of acceptance, and B, the numerical aperture? Let us start with A, the angle of acceptance. It can be computed with theta in max equals the inverse sine of the square root of n1 squared minus n2 squared over no. n1 is the index of refraction of the core, which is 1.55. n2 is the index of refraction of the cladding, which is 1.45. n0 is the index of refraction of the external medium, which is an air medium, and the index of refraction of the air is 1. Substituting the values, we get theta in max equals 33.21 degrees. For B, we find the numerical aperture using the formula Sin theta in max equals the square root of n1 squared minus n2 squared over n0. Again, we just substitute the index of refraction of the different materials and we get Na equals to 0.5477. One kind of a fiber optic cable is the flat ribbon cable. It works well with multiple fibers. It provides for easy handling and identification of individual fibers. It is space efficient for some applications. A PCS cable is short for plastic clad silica cable, which is a glass core with a plastic cladding. Here is the standard colors for the ANSI, TIA, EIA 598B. For fiber or unit numbers 1 to 12, the fiber color is blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, and aqua, respectively. For 13 and higher unit numbers, the color code is repeated. Black stripe or dash is added according to the ANSI or TIA or EIA 598B specifications. That means for fiber unit 13, the fiber color would be blue and black stripes, for 14, orange and black stripes, and so on. Fiber optic cables can be classified in two ways, 1 by index and 2 by mode. By index, we look at the index of refraction of the core. By mode, we look at the number of propagation paths. Under by index, we have the step graded index and the graded index cable. In the step index cable, there is a step in the refraction index from the core to the cladding. The core has a greater refraction index than that of the cladding. In the graded index cable, the core has a gradient in the index of refraction. In the center of the core, there is maximum index of refraction, and then as you go towards the ends of the core, there is lesser index of refraction. By mode, we have single mode and multi-mode. In single mode, light travels in one path through the fiber optic cable, while in multi-mode, instead of traveling in a single path, the light rays can travel in different paths. The light travels in multiple paths. That's why it is called multimode. Single mode step index cable. In a single mode step index cable, both core and cladding have constant index of refraction. Light travels in one propagation path, straight line end to end of the fiber optic cable. It is widely used for long distances. It eliminates modal dispersion by minimizing the paths through the core. Minimum refraction results to little pulse stretching. Output pulse have the same duration as input pulse. High pulse repetition rate with maximum amount of information. The typical core sizes in a single mode step index cable are 2 to 15 micrometers. Here are the advantages and disadvantages of single mode step index cable. The first one for the advantages is minimum dispersion. All rays propagate down the fiber and take the same path. Therefore, it takes approximately the same amount of time. Therefore, minimum dispersion. High transmission rates. Due to the high accuracy in reproducing transmitted pulses, larger bandwidths with high transmission rates are possible. For the disadvantages, the first one is small center core. Because of the center core being small, it is difficult to couple light into and out of the fiber. In addition, a highly directive light source is required to couple light into the fiber. It is also difficult to use. And lastly, it is high cost. It is expensive and difficult to manufacture. Single mode step index cable. In a single mode step index cable, both core and cladding have constant index of refraction. Light travels in one propagation path, straight line end to end of the fiber optic cable. It is widely used for long distances. It eliminates modal dispersion by minimizing the paths through the core. Minimum refraction results to little pulse stretching. Output pulse have the same duration as input pulse. High pulse repetition rate with maximum amount of information. The typical core sizes in a single mode step index cable are 2 to 15 micrometers. The next type is a single mode graded index cable. This type is not a standard fiber optic cable. It is not discussed in most textbooks. It is used for specialty applications. The graded index profile is normally non-parabolic. The next type of fiber optic cables is multi-mode step index cable. It is the most common and widely used type. Inside the cable, light takes multiple paths, which causes dispersion. Multi-mode step index cable is the easiest to make, thus the least expensive. It is widely used for short to medium distances at relatively low pulse frequencies. Its main advantage is its large size. The large core diameters are excellent at gathering light and can be used with inexpensive light sources such as LEDs. Typical core diameters are in the 50 to 1000 micrometer range. Here are the advantages and disadvantages of multi-mode step index cable. Advantages: low cost. It is inexpensive and easy to manufacture. Large source to fiber aperture. It is easy to couple light into and out of the fiber. Disadvantages: multiple paths. Light rays take different paths down the fiber. Therefore, they have large differences in propagation time. Distortion. Pulse of light propagating down is distorted due to multiple paths. Furthermore, it has less bandwidth and low information transfer rate. The next type of fiber optic cables is multimode graded index cable. The light rays have multiple curved paths of transmission. The light rays repeatedly converge due to the varying index of refraction. All light paths converge and tend to arrive at a point simultaneously. It has less modal dispersion. It also has high pulse rate with considerable amount of information. The core sizes are typically in the 50 to 100 micrometer range. It is easy to use, easy to splice and interconnect with less intense light sources required. Optical multimode, or simply OM, is the most popular kind of graded index multimode fiber. It is standardized by the TIA or EIA. It is used for shorter ranges such as small campus or multi-floor buildings. It handles most common data rates from 1 GB per second and 10 GB per second up to 100 GB per second. Limited data rate. Optical multimode has limited data rate per unit of length due to dispersion. The bandwidth is the frequency point wherein the optical power level drops to -3 decibels relative to the zero frequency power. Here is a table depicting the different OM cables. The first diameter is the ratio of the core diameter and the cladding diameter in units of microns. The second parameter is the effective modal bandwidth, or simply EMB, which is the data rate per unit of length. These cables are used in Ethernet at different speeds and distances. OM1 has the ratio of 62.5/125 and the effective modal bandwidth is 200 MHz kilometers. OM2, the ratio is 50/125 and the EMB is 500 MHz kilometers. OM3 has the diameter ratio of 50/125 and the EMB is 1500 to 2000 MHz kilometers. OM4 has a diameter ratio of 50/125 and the EMB is 3500 to 4700 MHz kilometers. The next topic is losses in fiber optics. The first type of loss is absorption loss. Light is absorbed the impurities in the fiber and converted to heat. This is analogous to power dissipation in copper cables. Ultra-pure glass used to manufacture optical fibers is approximately 99.9999% pure or 99.49% pure. But still, absorption losses between 1 and 1000 decibels per kilometer are typical. Three factors that contribute to absorption losses are ultraviolet absorption, infrared absorption, and ion resonance absorption. Ultraviolet absorption is caused by valence electrons in the silica material, from which fibers are manufactured. Light ionizes the valence electrons into conduction. Ionization is equivalent to a loss in the total light field and, consequently, contributes to the transmission losses of the fiber. On the other hand, infrared absorption is a result of photons of light that are absorbed by the atoms of the glass core molecules. Absorbed photons are converted to random mechanical vibrations typical of heating. Ion resonance absorption is caused by hydroxide ions or OH negative ions. The hydroxide ions come from water molecules trapped in the glass during the manufacturing process. It is also caused by iron, copper, and chromium molecules. Next to absorption loss is material or Rayleigh scattering losses. Diffraction happens due to impurities in the fiber, which causes light to scatter or spread out in many directions. Some light may escape through the cladding and light power is lost. These impurities are submicroscopic irregularities permanently formed in the fiber due to the manufacturing process. The next type of loss is radiation loss. It is caused by small bends and kinks in the fiber. There are two types of bends, microbends and constant radius bends. Microbending occurs as a result of differences in the thermal contraction rates between the core and cladding. In other words, the core might contract at a different rate than the cladding. Microbend represent a discontinuity in the fiber where Rayleigh scattering can occur. Constant radius bends occur when fibers are bent during handling or installation. Coupling losses can occur at any of the following three types of optical junctions: light source to fiber connections, fiber to fiber connections, and fiber to photodetector connections. Junction losses are most often caused by one of the following alignment problems: lateral misalignment, gap misalignment, angular misalignment, and imperfect surface finishes. In lateral misalignment, there is lateral or axial displacement between two pieces of adjoining fiber cables. The more it is aligned, the greater the loss of light. Gap alignment. This is also known as end separation. In splicing where two fiber ends are fused together, the fibers should actually touch. The farther the fiber ends are apart, the greater the loss of light. Angular misalignment. This is also known as angular displacement. The axes of the two fiber cables are not aligned, which causes loss. The next one is imperfect surface finish. The ends is not polished and does not fit when two fibers are adjoined.
Now, we are going to talk about dispersion. Dispersion is one of the losses in fiber optic cables. Dispersion is the distortion of the optical signal due to the characteristics of the cable. It has four types. First is the modal, next chromatic, next is the polarization mode, and the material and waveguide. So this phenomenon is due to the fact that speed of light depends on its wavelength and propagation mode. In case of traveling long distances, slight differences in speed accumulate. First is the modal dispersion. It is the stretching of the pulse due to the different arrival times of various light rays having different traveling paths. Because of modal dispersion, input pulse cannot occur at a rate faster than output pulse permits, otherwise the pulses will essentially merge. Only cure is to reduce the pulse repetition rate or pulse frequency, which renders proper operation to occur. Next is that the downside in this is that low frequency can handle less information. The key point is that the type of cable selected must have a modal dispersion sufficiently low to handle the desired upper frequency of operation. Pulse spreading constant or delta small t. The time delay between the fastest and slowest rays of light propagating down a fiber caused by a length of the fiber in ns or over km. The total pulse spread or delta big T expresses how much in time is the pulse spreaded due to the time delay between the fastest and slowest rays. The maximum data transmission rates. For UPRZ, the given formula is 1 over delta T times L. And for UPNRZ, the given formula is 1 over 2 times the delta T times L. Sample problem number 1. For an optical fiber of 8 kilometers long with a pulse spreading constant of 4.4 ns over km, determine the maximum digital transmission rates for A. Return to 0 and B. Non-return to 0. Chromatic dispersion. It occurs when the multiple wavelengths of lights are used, as in dense wavelength division multiplexing DWDM systems. It is also called as the pulse spreading, since the pulse stretches occurs since the higher light frequencies travel faster than the lower light frequencies. It is caused by a delay differences among the group velocities of the different wavelengths composing the source spectrum. It is the most troubling at data rates above 10 gigabytes per second. Polarization mode dispersion. It is the pulse stretching that happens in single mode fiber or SMF. In SMF, pulses are transmitted in two distinct polarization modes, and the electric fields of two modes are perpendicular to each other. Pulses with different polarization orientations can travel at different velocities in different parts of the cable, which is caused by bending and other distortions. It measures in picoseconds, which does not affect pulses at rates under 5 gigabytes per second. Above 10 gigabytes per second, specifically in long haul ones and in MANs, PMD is noticeable. Material and waveguide dispersion. For the material dispersion, it is caused by a change in fiber optic material's refractive index with different wavelengths. The higher the index, the slower the light travels. It is undesirable to change due to the desirable intrinsic properties of chosen material for optical fiber, most likely silica. For the waveguide dispersion, it is due to the distribution of light between core and cladding. Since waveguide properties depend on wavelength, changing the wavelength affects how light is guided along the fiber. Both material and waveguide are added together to form a zero chromatic dispersion at a desirable operating wavelength. The figure above shows how material dispersion, waveguide dispersion, and chromatic dispersion vary with wavelength in non-zero dispersion shifted fiber and indicates zero chromatic dispersion at 1.5 micrometer wavelength. Dispersion compensation. Although optical fiber dispersion does not weaken the signal, it shortens the distance the signal travels inside optical fibers and blurs the signal. There are three primary techniques for compensation. First is the dispersion compensating fiber the fiber Bragg grating, and the electronic dispersion compensation. Dispersion compensating fiber. Using a fiber with large negative dispersion alongside a typical fiber, it contains a large value of dispersion of opposite sign to reduce the light distributed by the traditional fiber. It has three primary schemes: the pre-compensation, post-compensation, and the symmetrical compensation, as seen in the figure. Fiber Bragg grating. It is a reflective device composed of an optical fiber that contains a modulation of its core refractive index over a definite length. Are passive optical element fiber compatible, having low insertion losses and prices. Electronic dispersion compensation. It is a method using electronic filtering, also known as equalization, to compensate for dispersion in an optical communications link. It can be used both in single-mode fiber systems and multi-mode fiber systems. It is typically implemented with a transversal filter, the output of which is the weighted sum of a number of time-delayed inputs.
Now, we will be discussing the free space optics, or the FSO. First, let us discuss what the free space optics is. Now, the FSO is a wireless, point-to-point, fiberless, laser-driven, and line-of-sight optical communication technology that uses invisible light propagating in free space to transmit information. Now, the FSO can transmit data, voice, and video simultaneously through the air. Furthermore, it can transmit at a speed of 1.25 gigabits per second at a distance of 6.4 kilometers in full duplex mode. Now, how does the free space optic work? The FSO technology uses a pair of FSO units consisting of an optical transceiver. There is a laser transmitter and a photodetector receiver that provides full duplex communication without the fiber. So now, we will discuss the key characteristics of free space optics. So first, the link can be installed and aligned in less than an hour. The full installation does not take more than 1 day. The FSO can be used in disaster management and emergency conditions. These systems employ powerful lasers that can transmit through glass and windows. The FSO also has the potential to become an effective means for last-mile delivery of telecom services. It offers fast and high return on investment. The FSO AL spectrum is nearly unlimited, thus very dense frequency reuse is possible. This makes it very convenient deployment of FSO systems worldwide. The FSO is also immune to radio frequency interference or saturation. It also has a low latency, low jitter, and low bit error rate connections. The FSO also have a very small spot size. The spot size is the radius or diameter of the beam. The spot diameter is the angle which is expressed in milliradians times the range which is expressed in kilometers. And the small spot size makes the FSO hard to intercept, making it ideal for high security applications. So there are different free space optic network topologies. First, we will discuss the point-to-point connection. The point-to-point connection topology is where two devices or nodes have a single path for data to travel between them, without anything to break up the path. Next is the star topology. In the star topology, all devices are connected to a central hub utilizing independent links. In this topology, the central node or device is usually a hub or a multiplexer that utilizes repeaters to forward data. Next is the ring topology. In the ring topology, all nodes are connected to one another in the shape of a closed loop. Now each node is connected directly to other nodes. Lastly, we have the mesh topology. In the mesh topology, devices are connected with many redundant interconnections between networks. Here, each node is connected with 2 to 4 nodes and is able to receive, transmit, and forward data packets. It is important to know that all topologies comprise a combination of P2P links. So there are various challenges in free space optics. Here, we will discuss the environmental factors. So first is the fog. The fog is composed of water droplets between a few and 100 microns in diameter. This allows absorption, scattering, and reflection to occur when laser beams pass through it. Now, fog is a major challenge to FSO communications and can result in atmospheric attenuation of signal. Especially with heavy fog, this can result in a complete outage of the service. Next is the low clouds, rain, snow, and dust. Low clouds are very similar to fog and may accompany rain and snow that may significantly degrade optical signals. Next is the rain. The rain can also degrade the performance of an FSO transmission. Raindrop sizes are larger than fog, so this may cause scattering of optical signals as well. Extremely heavy rain can entirely disrupt the link. Water sheeting on windows can also deteriorate the signal. Next is the heavy snow. Now, heavy snow may cause whiteout conditions and may result in ice buildup on windows. Laser beams are affected by heavy snow and rain that can cause attenuation to the laser beams of 60 to 1000 decibels per kilometer. Last is the sandstorms. Now, the sand or dust particles can alter the signal path to a finite extent. In desert areas, sandstorms occur very often, but they occur rarely in urban areas. Next, we have the atmospheric conditions. So first is the absorption. Absorption occurs when suspended water molecules in the terrestrial atmosphere extinguish photons. This causes a decrease in the power density of the FSO beam and directly affects the availability of telecom services. However, the typical wavelength values of FSO systems are 785, 850, and 1500 nanometers. Now, these wavelengths correspond to atmospheric windows where the attenuation is very small. Thus, the absorption attenuation is also very small. Next is the scattering. The scattering is caused when a light wave collides with the scatterer. The physical size of the scatterer determines the type of scattering. When the scattering is smaller than the wavelength of the light, it is known as the Rayleigh scattering, which occurs due to atmospheric gas molecules. Now, when the scatterer is of comparable size to the signal wavelength, Mie scattering occurs. This is particularly caused by aerosol particles. Lastly is the scintillation. Heated air rising from the earth or man-made devices such as heating ducts create temperature variations amongst the different air pockets. Now, propagation through air pockets of varying temperature, density, and refraction index causes beam spreading and wandering. Scintillation is temporal and can cause spatial variation in light intensity, which leads to increased error rate but not complete service outage. So there are other challenges in the free space optics. These other factors include the physical obstructions, building sway or seismic activity, and window attenuation. So for physical obstructions, flying birds or some temporary obstruction in the path of FSO signal can temporarily block a signal optical beam. But this tends to cause only short interruptions, and transmissions are easily and automatically resumed. Now, building sway or seismic activities, the movement or swaying of tall structures, buildings due to the winds, coral mine blast, and seismic activity can upset receiver and transmitter alignment. Usually, building sway is not more than 4 to 10 milliradians, but such a small misalignment can also increase bit error rate. In such situations, beam divergence is kept larger than expected building motion. Automatic pointing and tracking is the best option for exploiting optimum performance of an FSO system. Lastly, we have the window attenuation. In some cases, where high altitude rooftop weather losses are more, FSO systems are installed in windows. But it has been observed that uncoated glass attenuates almost 4% of signal per surface due to reflection. Tinted or insulated windows can have much greater attenuation. So, a trade-off between those two options, the window or rooftop installation, should be achieved. So these are some applications of free space optics. First, we have the WANs or wide area networks and crosslinks. We also have the point-to-point LOS or line of sight links. We also have spacecraft and satellite communications, as well as military applications.
Light sources and light detectors. The light sources must be high speed. It cannot use incandescent lamps. The two most commonly used light sources for fiber optic communications are LEDs or light emitting diodes and laser diodes. The physical arrangement of an LED is shown on the left, where the radiation is occurring from the P-type material around the junction. Light radiation of LEDs are shown on the right. For the LEDs, it is a PN junction semiconductor device that emits light when forward biased. Its semiconductor material is usually made of aluminum gallium arsenide or gallium arsenide phosphide. It emits light by spontaneous emission, wherein light is emitted as a result of recombination of electrons and holes. The simplest LED structures are homojunction, epitaxially grown, or single diffuse devices. Epitaxially grown LEDs are usually constructed with the use of silicon-doped gallium arsenide. Planar diffused or the homojunction LEDs are non-directional of its light emission, and the planar heterojunction LEDs are similar to epitaxially grown LEDs. LEDs can be designed to emit virtually any color of light desired. LEDs are also used for fiber optic transmission, which are usually in red and near infrared ranges. Typical wavelengths of LED light commonly used are 0.85, 1.31, and 1.55 UM. More commonly designated at 850, 1310, and 1550 nm, where 1 micrometer is equal to 1000 nanometer. For the light sources, the next one is the laser diodes. It emits monochromatic light. Monochromatic light is a pure single frequency light. Coherent, all light waves are emitted in phase with one another. Coherence produces a focusing effect on a beam so that it is narrow and, as a result, extreme intense. It is also known as Fabry-Perot or FF or FP laser. A PN junction diode usually made of gallium arsenide. Its physical structure is a semiconductor structure is cut into square and at the ends form a internal reflecting surfaces. One of the surfaces is usually coated with a reflecting material such as gold, and the other surface is partially reflective. When the diode is properly biased, the light is emitted and bounces back and forth internally between the reflecting surfaces. The distance between the reflecting surface and the distance between the reflecting surfaces has been carefully measured so that it is some multiple of a half wave and at a light frequency. The bouncing back and forth of the light wave causes their intensity and reinforce and build up. The structure is like a cavity resonator for light. The result is an incredibly high brilliance, single frequency light beam that is emitted from the partially reflecting surface. The physical structure, as said earlier, is a semiconductor structure that is cut into square and at the ends form an internally reflecting surfaces. One of the surface is usually coated with a reflecting such as gold. The other surface is partially reflective. When the diode is properly biased, the light is emitted and bounces back and forth, as said earlier. For the DFB or distributed feedback laser, it solves the problem of interface of FPILD. It is made with a cavity that contains an integrated grating structure that acts as a selective filter. The output from A. It has a narrower bandwidth and is nearer to a single light wavelength than any other type of laser. FP and BFB lasers are high-power lasers made and are used primarily in long-distance fiber transmissions and in metropolitan area networks. The vertical cavity surface emitting laser or VCSEL. Instead of emitting light from an edge of a diode, the VCSEL is made on the surface of silicon wafer like transistors are integrated circuits. The cavity is vertical to the wafer surface so that the light emitted from the surface. VCSELs are very easy to make and it is low cost. They can be made in arrays on the wafer surface. The output power emitted by the VCSEL is greater than of the LED but less than of the FB and the DFB laser. Its bandwidth is less than the output of the LED also and has a wider than either of the FB or DFB laser. This makes VCSELs ideal for short distance LANs or MANs. Most VCSELs are 850 nanometers, but recently 1310 nanometer VCSELs came available. For tunable laser, a recent development is a tunable laser whose frequency can be varied by changing the DC bias on the device or mechanically adjusting an external cavity. A wavelength range of more than 100 nanometers above and below a center frequency is possible. Wide-range tunable lasers are being developed. Tunable lasers are used in applications where multiple frequencies are needed, as in dense wavelength division multiplexing, or the DWDM. Instead of having to inventory many expensive lasers, each on the separate wavelength, a single laser or at most several lasers are adequate to cover multiple frequencies. For the light detectors, receiver part of a optical communication system. It senses light pulses and converts them into electrical signals. The examples are photodiode, phototransistor, and pin diode. Let's start with the photodiode. A photodiode is a widely used light sensor. It is a silicon p-n junction diode that is sensitive to light. It is normally reverse biased. When light strikes the diode, leakage current increases significantly. The current develops a voltage drop across the resistor, resulting to a output voltage pulse. Small reverse current produces a small voltage pulse that must be amplified. For a phototransistor, it is the most widely used light sensor. Silicon p-n junction diode that is sensitive to light. It is normally reverse biased. When light strikes on the diode, leakage current increases significantly, as I have said earlier. And a small reverse current produces a small voltage pulse that must be amplified. Next is the phototransistor. It is more sensitive to light than the p-n junction photodiode. It is a base collector junction that is exposed to light, and the base leakage current produces and causes a large emitter to collector current to flow. Although it is more light sensitive, they are relatively slow. Further amplification and pulse shaping is needed. The pin diode, it is an improved p-n junction photodiode with an added undope or intrinsic layer between the P- and the N-type region. It has an increased sensitivity and decreased response time relative to photodiode. The thin P layer is exposed to light, which penetrates to the junction, causing electron flow proportional to the amount of light. This diode is also reverse biased, significantly faster in response to rapid light pulses of high frequency, and their light sensitivity is far greater than that of a ordinary photodiode. Avalanche photodiodes. It is the most widely used photosensor. It is the fastest and most sensitive photodiode. However, it is expensive and has most complex circuitry. It also has a reverse bias, but it has a different operation. It operates in the reverse breakdown mode like the Zener diodes. When light strikes the junction, breakdown occurs and a large current flows. It requires less amplification. Germanium APDs are significantly faster than the other diodes and are capable of handling the very high gigabit per second data rates.
Here are the summary of concepts of the fiber optic cables. Optical communication systems use light to transmit information through free space or fiber optic cable. The study of optical communication systems using a free space medium is called the free space optics or FSO, and when fiber optic cable is used, it is called fiber optics. Optical communications uses the principle of optics. Optics is the study of light that is a form of energy in the form of an EM wave. Light can get refracted when passing a boundary between two transparent materials of different refraction of index. Snell's law relates the angle of incidence and the angle of refraction with the equation n sub 1 sine theta sub 1 is equal to n sub 2 sine theta sub 2. Light gets reflected by a reflective surface. Law of reflection states that the angle of incidence is equal to the angle of reflection. Critical angle is the angle of incidence where the refracted ray travels along the boundary of the two different materials. When the angle of incidence is below the critical angle, the light gets refracted. Above the critical angle, the light gets reflected. The index of refraction for air is 1, for water, approximately 1.3, and for glass is 1.5. The main components of fiber optic communication systems is the fiber optic cable and the light source and light detector. In the light source, there can be a source to fiber interface and an A or D converter. In the light detector, there can be a fiber to the light detector interface and a D or A converter. There is also an amplifier and shaper to take into account the attenuation and distortion that happen as the signal light traveled the cable. The main advantage of fiber optic communication system is its easy installment, wider bandwidth, and safety from shock hazards. Its main disadvantages are its high initial cost and its fragility as compared with other copper cables. Core, cladding, and jacket is the most basic elements in the construction of fiber optic cables. The jacket is for protection. The cladding is for the internal of refraction to occur since it has a different index of refraction with the core. The core is where the light propagates. The cone of acceptance defines what angles can a light ray enter the end of the cable so that it will undergo total internal reflection. The acceptance angle is the maximum angle of the angle of incidence as the light ray enters the end of the fiber cable that will make the light ray undergo total internal reflection. The acceptance angle has the formula theta in max equals the arcsine of the square root of n sub 1 square minus n sub 2 squared over n sub 0. The numerical aperture measures the light gathering ability of a fiber and is mathematically defined as the sine of the acceptance angle. Fiber optic cables can be classified by index and by mode. A step index cable has constant index of refractions for core and cladding, with the cladding having a lower index of refraction. A graded index cable has a graded index profile where the index of refraction of the core changes along the radius of the core. Single mode cable has one number of propagation paths for light. The multi-mode cable has multiple number of propagation paths. The multi-mode step index is the most common and widely used type. The losses in fiber optic cables are absorption loss due to impurities in the fiber that absorbs energy and dissipates heat. The Rayleigh scattering loss because of the scattering of light causing the escape of some light. The radiation loss that is due to the bending. Coupling loss due to the misalignment and imperfect surface finishes and the dispersion. Dispersion is the distortion of the optical signal due to the characteristics of the cable. It has four types: modal, chromatic, polarization mode, and the material and waveguide. Dispersion compensation. Although optical fiber dispersion does not weaken the signal, it shortens the distance that signal travels inside optical fibers and blurs the signal. There are three primary techniques for compensation: dispersion compensating fiber, fiber Bragg gratting, and electronic dispersion compensation. Free space optics, or FSO, can be used in disaster and emergency conditions. It can be used in one- and cross-link systems. The challenges in FSO are environmental factors, atmospheric conditions, physical obstructions, seismic activity, and window attenuation. Light sources in optical communication systems must have high speeds. It can be LEDs or laser diodes. Light detectors in optical communication systems is the receiver part of the system and can be a photodiode, phototransistor, or PIN diode. The next slide shows the summary of equations of the fiber optic cables. The formula for the wavelength is given as the lambda equals c over f, where c is the velocity of the wave and f is for the frequency. The given formula for the angle of acceptance is the theta in of max equals arcsine times the square root of n sub 1 squared minus n sub 2 squared all over n sub 0. The formula for the numerical aperture is NA equals sine theta in of max is equal to square root of n sub 1 squared minus n sub 2 squared. Total pulse spread is equal to pulse spreading constant times L. For the maximum data transmission, for UPRZ, the formula is equal to 1 over delta T times L, and for UPNRZ, the formula is equal to 1 over 2 times delta T times L.
And once again, this is topic 14 entitled Optical Communication Systems, brought to you by Joervie P, ADANTE, Aulivier Gilchrist Q, Aquino, Jarren S, BAYLON, and Denise L, BURGOS. We are from Group 9 of B11, and thank you for listening.